biggest reflection I have going back to Chris is how old my friends are getting. But no, it's fun. Anyhow, it's fun to be here, and it's been a great day talking with people, and look forward to discussing things with you more tomorrow, or later tonight, I guess. Today's talk is intended to be a little provocative, so hopefully I'll get some tough questions in response to some of it. Maybe you'll agree with everything I say, so that won't be the response. But the reality is, it's probably never been a more important time to be an ecologist in terms of figuring out what the heck we're going to do with the fact that humans are changing the world at rates that have been unprecedented, at least in our human, in the time since we've been around. Lots of stuff is going on. And of course, everyone has probably seen these data, the realization that there's no debate anymore. Anyone who says there's a debate with climate change, of course, is clueless. The question is, where is it going? And I think what's more important is not only how warm the world is going to get, but what is the impact going to be on ecosystems? Because the reality is, if it really is 3 degrees warmer, it may actually feel a little better than it is outside right now. But where the action is how are ecosystems going to respond? Because that's what humans are interacting with. We're depending on water, we're depending on a bunch of ecosystem goods and services that are going to be far more sensitive to climate change than what we might just, quote unquote, feel through a couple degrees of climate change. So what are we doing as ecologists? If we go back a second, we look at this trend in bi-decadal changes in temperature, you can probably map onto that the number of publications published by ecologists who motivate their papers with climate change or global and grappling with these issues in a real way. And what are the typical approaches that we're taking? I'm just going to run through a couple papers here. These are papers written by distinguished scientists that I have lots of respect for. One that came out a couple years ago that was really critical of fisheries management. Again, by some really top-notch ecologists, edited by another top-notch ecologist, and the last line of their abstract here is that we argue that fisheries science and management must follow this lead, which is really about understanding the intricacies of marine ecosystems in this case, by developing sharper species interactions of disrupting these interactions to push ecosystems in which embedded as tipping points. I mean, as ecologists and as biologists, the details are really what motivate us, right? That's why we're out in the field and measuring things and being surprised by things, etc. But I think we need to step back and ask in an honest way, how much are all the details really contributing to our ability to forecast the future, and how important are those forecasts for developing good policy? The message I have today is that our forecasts are always going to be lousy. Okay? Despite our best efforts, and I don't mean this to slam on science, but I think the reality is ecological systems are remarkably complex. We're always going to be living in a world that's riddled with uncertainty. And our forecasts, reasonable time horizon in the future are always going to be really poor. The question is that what we should be pushing off to policymakers, saying, just give us another $1 million for my research program and I'll fill in more details and my predictions will be even better, which is typically the approach that we use in ecology. To highlight another paper, this one I think is a really important paper for
anyone to read who's interested in natural resources. It was done by the late Ransom Myers in '98. And what he did here was took 47 published studies where the question was trying to parse out how environmental variation, and environment was either some climate signal or sea surface temperature or zooplankton abundance, some environmental covariate. And what they did was showed some correlation with recruitment in fisheries. So fisheries scientists, since its inception, have been trying to figure out why are some years good for fish and why are some years bad for fish. What Myers took was took 47 published studies, let them dial forward for 13 years, added 13 more years of data to them, and then retested those models and asked how many of the original statistically significant correlations were still good enough to be used in management of those fisheries. And the answer was 1 out of 47. More data should make things better, right? In this case, more data, these correlations disappeared. So either the correlations were spurious in the first place, and they might have been. Some of them were probably supported by reasonable hypotheses. Some of them were probably purely spurious. They stumbled upon them and happened to find a correlation that allowed them to reject with a p-value of 0.05. But there's other things that are going on as well. And one of them is this idea of stationarity, which is something we typically assume, which is that the interactions and the relationships between variables in the past is going to be what the relationship will be in the future, okay? So when we study ecosystems, we're trying to figure out, well, what's the effect of rainfall on plant growth or rainfall on community composition? And the assumption is if we understand that now, we will be able to project forward because the assumption is that relationship is stationary. And as people dig into this in many ways, whether it's fisheries science, whether it's water management, we realize that most ecological interactions are not stationary. The strength of those relationships is changing through time. In this case, what they're thinking about is relationships between, for instance, how much precipitation falls in a watershed and how much water is yielded out of that watershed. And what they're seeing is that as climate changes or as land use changes, the same amount of precip can yield different amounts of water coming out the bottom of the watershed. Stationarity is a really bad assumption in ecology, I think, because we're typically measuring a couple of variables that we can measure, and of course, all of those relationships are immersed in a, I don't want to use the word multitude, but almost infinite number of other relationships, many of which we never see. So stationary is not a good assumption, and that really limits our ability to forecast the future. So my criticism is that what we typically have done within the sciences realm of ecology is really advocate what I call a predict and prescribe approach, where more investments and more will produce better science, and what I mean by better science is more detailed understanding. And the fantasy here is that better understanding produces better forecasts, and that's what policies should be developed around, is the way we forecast the future. We're going to say Great Salt Lake is going to have X amount more water in it 100 years from now. These are the management regimes that should be in place to enable whatever we want out of Great Salt Lake. So the argument is that a predict and prescribe approach, which is really a bit of medical envy in my view, where you go in, you feel sick, the doctor takes a few measurements, says this is what's wrong with you, take these tablets and you'll feel better in a week. So there's the identification of the problem, the prescription of the solution, but of course, what's the last thing the doctor tells you as you walk out the door of the office? Call me in the morning, call me next week and let me know how it worked out. I mean, the reality is that every doctor who prescribes you something is doing a little experiment on you. They think they know what's going on. They're going to give you what they think is the solution, but they're really not sure, okay? And in ecology, we like to think of ourselves as the doctors who are going to identify the problem, make some forecast about how it's going to respond to some prescription. But, let's get realistic. Our ability to really diagnose problems is really, really limited. So what we need to do is think about ways that we can be involved in the game, because we have a lot to contribute, okay? And figure out what's the best way that we can contribute to developing management and policy that will maintain ecosystem services and biodiversity and all the things that are important to humanity. So how do we do that? I think one of the ways to think about this is we need to think about ways to disperse risk. Okay, so risk is what happens in the future that we can't really predict. Okay, so an analogy here is of the financial systems that we all are a part of. Okay, financial systems are remarkably complex. They have hundreds of different variables. Okay, and there's a lot of highly motivated people trying to understand the financial systems. They're motivated because they want to make $1 billion out of it. And you know, the best statisticians in the world are probably working on financial systems. What's the main strategy that investors use when they're exploiting the financial systems that we're part of? They don't make forecasts. You know, they make very vague forecasts. What they do is figure out, how do I distribute risk relative to return moving into the future? So now apply that analogy to an ecosystem. I would argue that an ecosystem is way more complex than our typical financial system, and we have really lousy data. You know, the financial system, they're getting a new data point on every variable every day. They can fit incredibly complex models to them. And at the end of the day, what do? They sort of bail on it and figure out, how do we distribute risk to the unknown of what's going to happen in the future? So ecologists should be asking this question more than we do. And then the last thing I'll argue here is that we need what I'm going to call robust policy. And the idea here is that you develop policies that will be effective independent of what the future turns out to be. And there are certain things where the best policy in the world is never going to fix the problem. But you know, we can think about whatever your favorite problem is that you work on, and you can ask, well, what types of ways can you implement a management policy that's going to keep the system in the game, given we don't know what the future is going to look like? So I'll step you through a few examples of this, mostly from my work in Western Alaska. It's a really neat spot. It's up, here's Bristol Bay. It's the southeast part of the Bering Sea. It's a bit light here, but what's unique about this place are a whole bunch of really large lakes and rivers. There's almost no development here. These are essentially pristine rivers. Been heavily glaciated. It's this huge overburden of gravel. This is probably the most productive salmon ecosystem in the world. Sockeye salmon, the ones that turn bright red, about 50% of the world's sockeye comes out of Bristol Bay. A little bit comes out of Canada, a bunch comes out of Russia. This is really Mecca for at least for sockeye salmon. And people, oh yeah, and then on top of that, it's been one of the fastest warming places in the world. So University of Washington has worked here since the 45, and you know, we've invested in some long-term monitoring there. During this time period, we've had both highly motivated or high exploitation rates in the fisheries, simultaneous with a lot of climate change. So now we can retrospectively look back and ask, well, how did the systems change in ways that we may be able to draw some general principles out of? So here's sockeye salmon, really neat creature, tastes really good. It's worth something like $1.5 billion a year, which for, you know, most of that money does leave Alaska, but for Alaskan communities, it is huge in terms of its revenue. Those salmon also support a bunch of ecosystem services. There's a lot of bears here, for instance. A lot of people come here to view brown bears, and of course, all they're eating is salmon, et cetera, et cetera. So this is really an important species in these watersheds. And if we want to try to understand, well, how did salmon respond over the last half century to climate change, we really need to appreciate that how the habitat's structured that they use. Okay, so the fish are spending about half their lives in the North Pacific, either in the Bering or down here in the Gulf of Alaska, and they swim around the peninsula and come back to the lakes. And then they separate out into the 9 major rivers of this region. Each one has its own genetic stock of salmon that come back to it, they have their own life history strategies. And within each of those rivers, there's dozens to even hundreds of individual populations, many of which are genetically distinct. Okay? And all of these genetic distinctiveness is really mapped onto individual characteristics of the habitat, and some of which we understand, a lot of it we don't. So let's look at what fish returns have done here in the last, this is the good data from about 1961 through to almost the present here. And what you can see is that It depends if you're a glass half full or half empty person, but in general, there's been about 45 million fish that have returned to this system through time. It has been hammered. The exploitation rates here are somewhere between 50 and 70% per year. So 50 to 70% of the fish are harvested before they spawn. It's a very intense predation rate, or, well, it is a predation rate, I guess. But the number of fish that come back keep ticking along. And this is a time period where there's been 2 degrees of climate change over this time period. So what's gone on? Why is the system stable? I mean, certainly there are some peaks and valleys here. But one of the most interesting things that we've appreciated out of this, so each color is the number of fish returning to each individual river. And of course, what you can see is that the composition of the colors has changed dramatically through time. And from a conservation standpoint, back here in the 60s, this yellow one, the Kvichak River, was really where most of the action was. And if you ask the managers or the natives who lived here or the fishers, what's the most important river in Bristol Bay, they would all say the Kvichak is the one we have to protect. This is where all the action is, this is where we're making all our money, etc. Well, they could have easily walked away from all these other rivers, and they didn't because there wasn't any development pressure. Well, guess who's in the game down here? The Kvichak is still there, but in some years, it's maybe 5 or 10% of the total abundance of fish. And rivers that were essentially, economically barely viable are now the big ones. So Igigik is one. These are all weird names, but anyhow, the point is that the composition of the catch has changed through time. It's the same region. This is not a very big region. Okay, so what's gone on here? And why is this a sustainable fishery? So when people talk about sustainable fisheries, one of the first examples that they typically point to is Bristol Bay, Alaska. Salmon that's been hammered for 120 years, but the fish keep coming back. And in fact, the fisheries and the economies that are associated with are doing quite well. So how is that possible? Especially when we look at returns to an individual river. So here is, what I've done here is standardize the returns of this single river to the average, which is 1, and then that's 10% of the long-term return, and that's 10 times the long-term return. So for this individual river, it's bounced around between average conditions to 10% of its average to 2 or 3 times its average. And if you were a fisher exploiting this population, this would be a hard way to make a living. If you're a grad student and this is your monthly income, you probably don't stick around USU very long. So how can this system be sustainable? And the reason it's sustainable, I think we can appreciate if we overlay the other rivers and returns in the region. Each color now is a different river, and you can see that some of the ups and downs are synchronous, but many of them are not synchronous. So when some rivers are crashing, they're compensated by other rivers that are right next door doing really well. And what the fishery sees is that line. That's the integral of all those different rivers. So we use this term portfolio effect to describe the fact that the individual pieces are much more variable than the aggregate. And by fishing the aggregate, what the fishing industry has done implicitly, they haven't done this on purpose, it's implicit, is they've distributed their risk to the effects of climate on these different watersheds, even though they're still all experiencing the same regional climate forcing. Okay? It's been sustainable for 120 years, and there hasn't been a lot of science that has gone into that management. The management is still very simple, and I'll talk about that in a sec. So let's build that up a little bit. This is the same time series I showed you for the aggregate of Bristol Bay. Here are the major rivers. This line right here is the 1 line. That's 10%, 1%. We then have data from our long-term surveys in one of the rivers to look at individual streams. And here we see that individual streams can go from 1 or 2% of their long-term average to almost 10 times their long-term average, depending on what year you're talking about. And even in the same watershed, the streams aren't going up and down synchronously. Okay? And then within each stream, we can break it out into individual age categories of the salmon. So a female salmon will lay her eggs in the gravel. They'll come out of the gravel the next spring, and then they spend either 1 or 2 years in freshwater before they go to the ocean. And then they return to spawn either after 1, 2, or 3 years in the ocean. So in effect, what she's done is distributed the risk of an uncertain future across 5 different years of those fish coming back to spawn. Okay? So then if we ask, well, if if the population didn't have this diversity in age comp, what would the variability look like? And now we're going from less than 1% of the long-term average in a given year to as much or over 10 times the long-term average. At fine scales, things are really variable. It's only at the aggregate scales do things become relatively dependable. As scientists, this is typically where we're doing our work. You know, we're working at fine spatial scales because that's where we can actually parse things and do experiments. But we're really trying to make predictions about what's going to happen at the aggregate scale. And despite a lot of efforts in these streams, we still don't have a good reason for understanding why some populations go up and others go down. So one criticism of what I just showed you is that what I'm emphasizing here is the year-to-year buzz in the data. And that if we start thinking about the future, really what we need to do is think about how dynamics play out over decade to century timescales. And maybe at those scales, things become more coherent across the region. So that if we're going to forecast out 100 years, maybe this diversity doesn't really matter. And so we use some of the tricks that Janice uses, some paleolimnology, to ask this question here is whether this diversity, this response diversity among salmon, plays out at century scales. And we use paleolimnology. You drop one of these things into the bottom of a lake. It comes up with a core of sediments. And for those who don't know, lake sediments are deposited at the bottom of the lake. They're buried by sediments from the next year. Those are buried from sediments the following year. And if you do it right, you could pull one of these tubes of mud up, slice it up, and you get a history of that lake. And then because salmon are coming back from the ocean where they put on most of their growth, they die after they spawn. All of the nitrogen in those bodies goes into the lake, and much of it is deposited in the sediments. And because these guys feed at a pretty high trophic position in the ocean, they have an enriched nitrogen-15 signature. So we can take one of these cores, slice it up, and from that infer how many salmon spawned in these lakes 200, 500 years in the past. So this is a synthesis we did that included lakes that in total are producing about 60% of the world's sockeye salmon, at least in the last century or so. And we asked this question, do we get response diversity over long time scales that we see across this region? So this is the summary of that. It's a busy figure, but I think the pattern is the general pattern is what I want you to see. For each panel, we have a single lake showing the last 500 years of N15, nitrogen-15 isotopes. And the higher the value, the more salmon are in there. The lower the value, the fewer the salmon are in there. The green lakes here are ones that have a waterfall. Fish haven't been in there as far as we can predict. And you can see they're all pretty smooth. They all show a little downturn recently. That seems to be a reflection of atmospheric nitrogen deposition. But you can see they're low and they're smooth. All the blue ones have salmon in them. And you can see they're much more variable. But if you just scan across that, you can ask, do I see a common pattern across all these lakes? And some of them, I mean, here are 2 lakes, or 3 lakes maybe, that seem to go up and down in synchrony. But you can see lots of different patterns depending on what pairs of lakes you choose. To do a little fancier analysis, we just do a principal components analysis on this and ask, well, is there a common pattern that's shared amongst all these lakes? And this is what it looks like. So here's the first 4 principal components. The only one that's significant is the first principal component. Okay, that's shared amongst all those lakes, and that's shown here in blue. And most of the action in the PC1 is this decline in the last 100 years. And this result has been misinterpreted by a few people to say, well, the fish crashed here. Well, the fish didn't crash here. The commercial fisheries developed around 1890, and all those fish, instead of returning to the watersheds and dying and being deposited in their sediments, were captured, stuck in cans, and sent to Britain. So, in fact, what this principal components analysis does is confirm our method, saying that the only thing that's shared amongst these lakes is this decline in salmon during the last century. You take that out of the game, and there's no significant trend shared amongst lakes in this region. So even at 500-year timescales, we get a lot of this regional response diversity. The same region, the same species, mostly the same types of watersheds are not responding the same way to the same regional climate signal. Is there a clock in here? Okay. So these arguments about variability, I mean, these make for great academic arguments. They give us papers, et cetera. But at the end of the day, we're hopefully helping people with some of this science. So the question is, do these differences in variability that we see as variability gets declines as you aggregate, does that reduction in variability actually have an influence on people? And it turns out we think it does in lots of ways, and I'll show you one example of this. And the way to understand this is to think about how the system is managed. Alaska Fish and Game does a really good job of managing these populations. Each stock is managed on its own, and it's managed around what's called an escapement goal, where based on the data on hand, they estimate how many fish does it take to saturate the spawning grounds in each river system. And let's say, so for all of Bristol Bay here, it's about 10 million fish is required to saturate all the spawning grounds. And then in any given year, any fish above that escapement goal are allowed to be, are caught by the fishery. They're allocated to the fishery. And the way the system works and the reason it's so effective is that if there are not enough fish to satisfy the escapement goal, there's no fishing. They just tell everyone on the radio, sorry gang, no fishing this year, go home. Which is a hard pill to swallow if you've been waiting around all year to go fishing and make your 50,000 bucks, pay your local taxes, put your kids through school, etc. So closing fisheries is a big deal. And there's no flexibility in it. They have emergency order and they just say no fishing if you don't achieve the escapement goal. So let's look at what variability looks like if we produce on average, in this case, 32 million fish, and we simulate the amount of variability that's currently in the system with all its complexity. And we just ask, well, how often do you not achieve the escapement goal? So in 100-year simulations, just due to random chance, despite the variance buffering, there were 4 years where they didn't achieve the escapement goal. And in this 100-year period, there would have been 4 years where people just wouldn't have been able to fish. So now let's take the same system, ramp up the variability to the level we think would be there if we strip out all the complexity in the system, but we maintained the same number of fish. And this is what we've done in the Pacific Northwest. We've turned our backs on habitat. We've assumed that we can produce the same number of fish from hatcheries. And it turns out the Pacific Northwest gets the occasional bumper crop of salmon, but most years are really bad. So this would be the strategy of a hatchery-dependent rather than a habitat-dependent approach to policy, and ask, well, how often would you close fisheries? And it turns out with the same average return, you're closing fisheries about 4 years out of 10, and you're starting to get strings of 3 or 4 years in a row with no fishing. So that's the level of change we're seeing in the variability of the returns when you have the intact complexity or portfolio in the system versus what happens when you strip it all out and everything is responding synchronously. So why is this possible? Why does this make sense? Because we like to think of, things of the same, species of the same species in the same general region should respond exactly the same to the same environmental conditions. And the reason I think, what we think is the reason we get this response diversity is, first of all, from population to population, there's genetic variation, and different genetic strains respond differently to the same environmental signal. So some of it is just pure genetic diversity. The other side of the coin is that the habitat is variable, okay? So fish aren't experiencing the overriding climate. Fish are experiencing the overriding climate as it's filtered through the local habitat conditions. So here are 4 different photos I've taken, each of which is a population catastrophe, okay? They're all within the same Wood River watershed, which is not a particularly big watershed, but they're different populations spawning in different tributaries. And this one here is, we call it Berm Creek because we came back one year to sample it, and this big gravel berm had built up at the mouth of this stream. So back here is a big lake. You can't quite really see it. But clearly what had happened is the last fall, the water level was high. There must have been a huge storm. The wave action built up this berm. And in a typical spring, when the snowmelt occurs, the stream floods, and there's enough energy to blow out that berm. So that when the fish come back to spawn in July, they just swim happily home, go up 4 or 5 miles, and that's where they spawn. Well, this was a year following a winter drought. The stream energy that spring was really low, and the water's trickling through there, but it never achieved enough energy to blow the berm out. And this is 4,000 or 5,000 fish who died right there, full of eggs, full of all their gonads, etc. The bears were happy, but as far as we can tell, very few of these things spawned. Here's a river just a few miles away, different year. And what we're looking at here is a bunch of dried up salmon nests. Okay, this was about half of this population. So what happened here is the fish spawn in late August, early September. And typically what happens in this part of Alaska is it starts raining in September and the water levels come up. Well, this was a fall drought. Okay, so that was a winter drought. Here's a fall drought. It didn't rain. This happened to be my sabbatical year, and I stayed till November up there. And late October, half the salmon nests had gone dry because it was just a fall. It was dry that fall. Okay, this stream did fine that year. This one didn't. Here's one. Here's a different little stream, a couple kilometers long. It had 80,000 fish in it a couple years ago. The stream is 3 meters wide and that deep. Unbelievable productivity. But here the fish have to swim over this little delta to get into the stream proper. They come out of the lake, swim across that, and into the stream. Well, the delta is about that deep, okay? It's literally an inch deep. And your fish are this big. They are literally crawling across this gravel to get into the stream. And if it's a summer drought, the water's way down here, and they have to make about a 100-meter run. And if it's a normal year or a wet year, the water level's high, and they don't have any delta to go over. Well, again, there's these furry brown things running around, and they'll kill half those fish on the delta before they get into the stream. There's a summer drought. Here's a beaver dam. The point is simply that different parts of the watershed are blinking in and out depending on how the habitat interacts with the overriding climate. Another example of how the habitat, this idea of a shifting habitat mosaic is a really nice paper that Jack Stanford and colleagues published a few years ago in kind of an obscure journal, but I encourage you to dig it out. And the idea is that fish habitat is a mosaic. I think we'd all agree with that. But the important part of it is that the mosaic is continuously shifting through time. It's shifting in terms of erosion and deposition processes, but it's also shifting in terms of what's productive based on how it's interacting with the overriding regional climate signal. So I'll give you a brief story here. I think Johnny Armstrong was here a couple years ago, and he told this story, but I'll tell it again because it's such a good story. It was part of his graduate work, but he worked in this stream here. And in this stream, there are 2 species of salmon. One is coho salmon, which spend about a year in the stream, fattening up, eating sockeye salmon. And they mostly eat sockeye salmon eggs, okay? And it turns out that within a single stream, and this is a second-order stream, it's a couple kilometers long, there's remarkable temperature heterogeneity in that single stream. So here's the outflow of the stream. It flows out of a meadow complex up here and then down to the lake. And there's a bunch of groundwater springs that come in at the bottom. And down here, the water temperature is on the order of 7 or 8 degrees Celsius. And up here in the beaver ponds and whatnot, it's up around 13 or 14 degrees Celsius. And then it goes through this abrupt transition. The sockeye that are the source of the food for the juvenile coho, they all spawn in the bottom of the stream where the water's nice and cold and full of oxygen. Johnny spent a lot of time crawling around in this thing, snorkeling. It's kind of, well, some of you have done some snorkeling in streams this deep. But the only place he found coho was way up there in the warm water. And he found that a lot of those coho up here had sockeye eggs in them. So there's 2 possibilities. Either the coho are going to the sockeye, which is about a mile away, and these coho are about this big, or the sockeye were swimming up to their warm areas to do something at night. So what he did was put some pit tag readers in here. These are just some antennas. You can put a little tiny tag in a fish. If it swims over that antenna, it'll pick up the number and the time of day, etc. So what did we find? I'll just show you one example. So this is a fish that was tagged in section 3, which is up at the top in the warm area. It sat around recovering for a few days while it dealt with this tag in it. And then about midnight one night, it blasted down, showed up on the middle antenna, blasted down to the cold area after swimming over the lower antenna, spent about 3 hours down there, turned around and went back up. This fish is the size of your finger, and this is a mile of stream, okay? It hung out there for 3 or 4 days, did the same thing. Hung out there for 4 or 5 days, did the same thing. I'm obviously showing you our best example, but most of the population was doing this. So what are they doing? Well, they're going to the food, all these rich, greasy little eggs by sockeye salmon that are just loaded with calories, but at 7 or 8 degrees, those coho can't digest those fish. So they swim back up to the warm habitat to digest them, put on a growth response. So a tiny little stream, you get contrast, you get heterogeneity in the environmental conditions, and the fish are exploiting it actively, and that's why they're growing fast and presumably having high survival rates. So Johnny's like, oh, this famous guy at Utah State, Wayne Wurtzbach, showed this for sculpin in Bear Lake, I think, in the 80s or something, that little sculpins were migrating up and down in Bear Lake to exploit the thermal heterogeneity. So Johnny's like, Wayne got it in nature, I'm going to get this in nature, but I need another year of data. So that was the year I showed you, and what I'm showing you here, the top trace is the upper water temperature, the blue is the lower water temperature. Nice contrast here. 2008 he did it again. Beautiful temperature contrast, warm at the top, cold at the bottom. The stupid bears ripped our antennas apart that year, so our data was kind of lousy. So we're like, all right, we got to do it one more year, and then we got a nice paper. So we did it one more year, and it rained like hell all summer. And when it rained, the water in the stream came out and washed out the temperature gradient. Okay, so there was so much water blowing through this stream that the top never warmed up, and it was the same, the bottom warmed up, the top cooled off. It was the same temperature down the Thalweg of the stream. So Johnny's a patient guy, and I'm an insistent mentor, and it's like, all right, let's do it one more year. So we do it one more year, and it rains like hell again. And there's no temperature regime difference between top and bottom. Luckily, he met a girlfriend who was sticking around in Seattle, so he's going to do it one more year. So he gets a 5th year of data out of it. It doesn't rain. We get a nice thermal regime difference. And what happens is that during this year, and this year, the fish are migrating. And during these 2 years, they don't show up on the antennas. They're not migrating. So based on the story I just told you, what you should all be thinking is, well, those were good growth years, and these were bust years, right? Because in the years that it flooded, there's no thermal regime for them to exploit. Well, it turns out they grew at exactly the same rate in all 5 years. So now we're thinking, all right, we're not even going to get a paper out of this, never mind submit it to Nature. So what happened? So this is where a lot of some nice natural history work and persistence by Johnny paid off, and this is a kind of a funky diagram, but I'll show you it here. This is the top of the stream. Each year is an individual, each string here is an individual year. The color corresponds to the temperature. So in 2007, here we have 12 degrees at the top. There's a transition down around 7 or 8 at the bottom. 2008, the same thing shows up. 2009 was the wet year, same temperature, cold everywhere. 2010, cold everywhere. 2011, it got the gradient again. So the question is, where are the fish? So if we look at the warm years first, we cut up the stream into these 200-meter sections, and the size of the dot tells you how many fish were observed in each of those sections. The color of the dot tells you what was the temperature of the water those fish were sitting in. And what you can see, except for a couple exceptions, in the dry years when you get the thermal regime, during the day, almost all these little coho were sitting in warm water at the top of the stream. Right? So that's where they're moving up, warming up during the day, and they make the occasional migration down to cold water to binge, and then get back up into the warm water. So what happened in the wet years? So in the wet years, here's our Thalweg, and now each of these spikes is off-channel habitat. Okay? So the stream flooded, it spilled over its banks, and now you have habitat outside the stream. Well, hindsight's always really clear, and in hindsight, what happened was, now you get off-channel habitat that warms up, and now all the fish are still sitting in warm water, but in this case, they're just going laterally out into the floodplain to warm up. So they're still exploiting the thermal regime, but the thermal contrast that existed in the dry year were different, at least their locations were different than in the wet years. So again, what you have here is a shifting habitat mosaic. The fish have this remarkable ability to figure out where they find the resources, and as long as they have the options, they make it work. And that's why the fish all grew at the same rate in all of those different years. So when we start doing things like asking, well, what's the critical habitat? What do we prescribe to the manager when we go to a new river and say, make sure that those habitat pieces are intact? We got to be really careful because what we're going to assign as critical really depends on what the conditions are when you assess what's critical and what isn't. And in the case of coho habitat, what coho exploit these remarkably complex wetland complexes, and what's critical in one year is not necessarily what's critical in the next year. So maintaining the diversity, maintaining the heterogeneity is one way to keep the options open for fish. Okay, I'll give you one last example about this shifting habitat mosaic at a slightly larger scale. So here again is Bristol Bay. The Nushagak River is a big river that flows out through this valley here. It supports a big Chinook salmon fishery. A typical year you get 150,000 Chinook salmon coming back here. No hatcheries, no nothing. This is Mother Nature in action, and they are nice fish. And they're all exploited down here in the estuaries. And here's the Nushagak River. For those of you who've heard about Pebble Mine is a massive copper gold mine that's proposed for the headwaters up here. And one of the big questions here is, well, what part of this vast watershed is producing all these massive Chinook salmon that have commercial fishing value and recreational fishing value, et cetera? And of course, the mining industry would love to say nothing's produced up in here. It's all in the western parts of the watershed. So Sean Brennan's a postdoc who actually does a lot of his analytical work down at University of Utah. But what he does is take otoliths, the ear stones out of salmon, ablates them with a laser, pulls the strontium isotope ratios out of them, and it turns out the strontium isotopes, even across a modest-sized watershed, change from tributary to tributary. So then he can catch a fish out there, or he can take a fish out of the commercial fishery, zap its otolith with a laser, figure out what the strontium isotope ratio is, and then put it on this map and determine what tributary produced that fish 5 or 6 years ago. And then we generate a heat map with some fancy statistics. But here's the Nushagak River, here's the outflow to the ocean. This is for 250 fish that were caught in the commercial fishery in 2011, and this is where they were produced. Little patch of habitat there. This is the King Salmon River. Why is it called the King Salmon River? Because it produces lots of king salmon, and sure enough, in 2011 it did. And here's the mine up here. Lots of white lines here, so that white means it didn't produce a lot. We could probably take this figure to the mining industry and say, how much do you want us to pay? How much would you pay us for this map? And I bet it's a big number, right? Well, we did it another year, okay? So we go back in 2014 and ask, does that same pattern hold up? And there's 2014. The King Salmon River was not a particularly good year for producing fish caught in 2014, but now the upper Mulchatna River is where most of the fish were produced. We worked so hard on this, I'm going to show you again. So there's going back to 2011, and there's 2014. The mosaic is there, and the mosaic is shifting. We don't really have a good understanding for why this is occurring, but so the question then is, well, what part of the watershed do you conserve and protect if you want to maintain fisheries here? Well, the answer is looking like you keep all of it, because at some point, different parts of the watershed are going to be used by this population of interest. So part of the message here, and we can apply this, one last example here is go to the marine system, and really this is the message that I think most ecologists appreciate and understand, which is that ecosystems are continuously changing. Dial back 30, 50, 100 years, and we talk about ecosystems as, it's tending towards some equilibrium state. But the reality is ecosystems are always reorganizing and bouncing around due to forcings of various types. And here's an example from the Gulf of Alaska. And these are experimental trawls from the same spot with the same gear at the same time of the year in different decades. And in the 70s, it turned up nothing but crabs and shrimp. There's a couple fish in there. In the mid-70s, they started seeing some halibut and pollock. Same spot, same gear, same everything. In the 80s, there was almost no crustaceans in that same catch, okay? We had a regime shift. It was all halibut and pollock, okay? So something massive changed in the ecosystem, was not predictable. In fact, they couldn't believe what they were seeing, and they kept monitoring, and then retrospectively, they realized, wow, the community changed. We don't know why. Here's some data from Alaska herring catches across coastal areas of Alaska. Each color this is analogous to what I just showed you for salmon, but these are different places in the ocean. Each one of these is a distinct stock. But here we get these boom-bust dynamics of herring stocks. Okay, different places are booming and busting at different times. Again, we don't necessarily know why. Tim Klein's a PhD student of mine who just had a paper come out 2 days ago, which actually exhibits a really, I think, important principle that we can think about when we come back to this idea of how do you distribute risk to the unknowns of the future. And what we did was look at another regime shift that occurred in 1989. And Nate Mantua and Steve Hare did a nice paper showing that if you just looked at environmental correlates or recruitment anomalies in the dominant fish species in the Gulf of Alaska, most of these things changed really abruptly in 1989, sort of a classic case of a regime shift. And then we have data from the Alaska Limited Entry Commission, where they track, so all Alaska commercial fisheries are permit required. You need a permit, a tradable permit to participate in any fishery. You can decide to sell that, but unless you have a permit, you can't fish. And the CFEC tracks the revenue and the catches of all these things. Anyhow, there's the 89 regime shift, and the catches mostly crashed there. But what this is what's called a dynamic factor analysis. It's like a PCA in time series domain. Each one of these is the loading of an individual variable, so an individual species on the trend that's shared amongst them. So this orange line is the trend that's shared amongst all the fisheries in Alaska, okay? But any individual species maps onto that basically with this correlation. So most of them are positive, which means most of them went down, but there's a bunch of negative ones, which means that even though a bunch of them went down, there were a few species that actually went up, so they showed the inverse of this shared trend. So what we're getting here is some buffering, like we expect to see in portfolio dynamics. So the question is, what happened to fishing communities? What happened to the people? And again, we can use the data to say, well, was there anything characteristic about the communities that affected their vulnerability to this massive regime shift? On average, your typical community lost half of its revenue in 1 year. And it was a combination of that change in the community and a change in market prices for salmon. But if we pick it apart to 100 different communities, this is the response. It's variable, but here's the diversity of species that are exploited within a community. And this is basically the percent change in their revenue following the regime shift. Most communities, here they are, lost about half of their revenue. These guys out here lost nothing. You know, this is the log of Simpson's diversity for the ecologists out there. But this value here is around 6 or 7 different species. So even if a community had a bit of diversification in it, it hardly budged after this massive regime shift in the environment. And if we take this a little bit further and ask, well, there's diversity, but there's also the ability for the composition to change, what happened? And you put it in one of these response surfaces, and you get a positive effect of diversity. And in this case, this is a little weird because it's the log of a negative number, but you get a positive effect of turnover. So the communities up here that actually benefited from the regime shift were those that had some diversity, but also had the ability to change the composition of the resources that they harvested. And you know, why some communities had that and why some didn't is really a question for social scientists, but the data tell us that those that could adapt were the ones that actually just rolled with the punches, or in some cases actually did better following the regime shift. Okay, so just to wrap up, part of my message is I think we need to think carefully about trying to project from what we've seen in the past to what's going to happen in the future. Because I think the future is going to be full of surprises. You know, we haven't been there before. We have new climate, we have new ocean acidification, we have new land use patterns, et cetera. The ocean and the land is going to be full of surprises. And we need to recognize this more clearly in how scientists give advice to policymakers. And the interesting thing is when we talk about resilience, it's a term that most ecologists use these days, you ask, well, what's a resilient system? Well, a resilient system is one that can absorb external perturbations, reorganize, but maintain its functioning. And that's what we see here at this last example with the different fisheries throughout Alaska. It's what we saw at the level of Bristol Bay sockeye fisheries. It's what we see at the fine scale details of coho salmon in Little Bear Creek. You know, the composition of the system, whether it's habitat or species, is turning over and changing, and that's what makes the system continue to function. So maintaining diversity in landscapes is a tangible way to manage risks of ongoing climate change, and really the message I think we need to talk about here is let's keep the options open for habitat and therefore for the organisms that inhabit that. Disturbances are really one of the main things that maintain habitat heterogeneity. So this is a stream that we've monitored forever. Came back one year and decides to take a new route. And if this was Washington, they'd have the dump trucks and bulldozers out there trying to put the river back in its channel. But of course, this is what rivers do. You got to let them walk around a little bit. And this is what generates the habitat variation that fishes have evolved to and exploit. And of course, everyone loves Aldo Leopold, and this quotation here is very well noted. I think the thing that I would add to this is that the cogs and the wheels are important, but what's equally important for at least for aquatic systems and especially for river systems is we got to maintain the processes that generate the cogs and wheels in the first place. And that means keeping flood regimes going, keeping disturbance regimes going, et cetera. And this is what we've done to rivers in the Pacific Northwest. Here's a reconstruction of the Skagit River, a big river north of Seattle, in terms of what the wetland complex looked like in the 1800s. Lots of colors here, mainly showing lots of diversity in hydrology and vegetation, et cetera. This is what it looked like in 1950 after a bunch of Dutch tulip farmers moved in and diked everything off and simplified it. And now literally tens of millions of dollars are going in to restore this thing to try to put the complexity back in there. You know, not surprisingly, the salmon aren't doing quite as well as they used to. But again, a lot of options have been taken off the table here for habitat and then also for the organisms that inhabit it. In the case of Alaska, Alaskans like to think of their territory is so vast and pristine that nothing's going on there. But here's a highway that went in along the Chena River up near Fairbanks. You can see the rivers meandering through here. But of course, what the river did here, what the highway's done here is basically take away a whole bunch of options for that river to continue to move and evolve through time. We don't need a lot of rocket scientists and deep understanding to start pointing our fingers at this sort of thing and say, this is not really a good thing to do to our river systems if we want to maintain resilient and productive systems. So to come back to this, accurate predictions are critical, are crucial. I think we should reject this. We don't need accurate predictions. Accurate predictions may be possible in some circumstances and will certainly benefit policy in those circumstances. But I think in most cases, we're going to be dealing with uncertainty. But that doesn't mean we should hang around and not do anything until better science rolls around. There's a bunch of first principles. There's a bunch of general phenomena that we can invest in that give us options into the future. And I'm running late, so I'm going to skip that. And I want to finish with this idea of scenario planning. This is something that's become fairly widely cited, mostly in social sciences literature. But it's actually an interesting way to think about the world, and that is that, in most cases, we're sitting here somewhere around time 0, and maybe we're at time 10, and we have a little bit of data, and we can make some forecasts about the future. We have some model that we're really proud of, and we can collect all the data needed to parameterize it. We do the fancy state space statistics on it, and we make forecasts about the future with confidence intervals and all the rest. And then the idea is that more data, more et cetera, maybe we'll tighten up these confidence intervals. And typically what we think about is that the uncertainty in our forecasts are associated with reducing the confidence bounds or increasing the precision of our favorite model. The thing that we've done in this case is we've really locked into a single worldview about what the system's going to do in the future. And in fact, what we've done as a result is exclude a whole bunch of possibilities for the way things may actually play out. So this type of approach would have totally missed, and it did totally miss, the dynamics that played out, observed in the real data as sort of Mother Nature played the cards out. So really what scenario planning does is use science, use thought experiments, use input from stakeholders, et cetera, to think about, well, what's the realm of possibility for the way the future may play out? And in some cases, it may actually look like this, based on logical arguments or science. In other cases, it may do that. And what scenario planning has been done, and this is a really interesting paper written mostly for the business community, but it's an interesting quote, which is saying, by identifying basic trends and uncertainties, a manager can construct a series of scenarios that will help to compensate for the usual errors in decision making. And these are what scientists, I think, typically do. Overconfidence in what we know, and tunnel vision. You know, we focus in on a single model or maybe a couple different models, and by doing that, we exclude the real uncertainties, which are the possibilities that a different model altogether may be actually in play. And a kind of a funny quote that's in that paper occurred apparently when the Navy was talking about ways to improve naval warfare. And Brigadier General Billy Mitchell, whoever that was, proposed that airplanes might be the most effective way as a defense against attack by battleships. And he was basically laughed out of the room. And what he was doing was thinking outside the box here. He was thinking that someday there's probably going to be airplanes around that are big enough to drop bombs on battleships from the enemy, and that instead of just focusing on how to make our own battleships more efficient and have longer missiles and this sort of thing, we need to think outside the box, think about other scenarios. And the response here by Newton Baker is, that idea is so damn nonsensical that I'm willing to stand on the bridge of a battleship while that nitwit tries to hit it from the air. Well, guess what we do now in terms of naval warfare? It's all through the air. And this is a situation where scenario planning, not knowing how the future is going to play out, may have produced, and eventually did produce, a very different result. Okay, almost done. So what's the precautionary approach? You know, this again is something that's widely cited in the ecological literature. And the way it's typically interpreted is, if you don't know about how the system's working, the best thing to do is sort of back off on it a little bit. Take it easy on it. If it's a fishery system, just harvest less and things will play out. Well, it turns out that is probably not the right way to think about the precautionary approach. And what the precautionary approach should be emphasizing is this idea of robust policy. Is thinking about what are the management systems that we can put in place that are going to keep working independent of which of these trajectories the ecosystem is going to take. We should also be thinking about ways to disperse risk, whether it's by distributing fish across a wider range of habitat, or figuring out financial ways to allow communities to fish many different species. Again, ecologists haven't thought about this too much. Monitoring and assessment, these two words need to come together, but you know, most people sort of glaze over when you talk about monitoring, but the reality is, instead of investing in a whole bunch of new fancy models and all the rest, we should make sure that we're continuing to monitor the resources that we're exploiting and depending upon. And science has a role to play in that. Good monitoring involves good science because you're always assessing the data that are coming in. And then the last is some flexibility. You know, if you have a management system that has no way to be flexible and change course, then it's probably not a robust policy. Oops. And with that, I'll finish and happy to take questions. Someone has to be pissed off. Chris.
So you sort of argue for trying to manage for diversity, but a lot of the data suggests that the amount of diversity changes tremendously over time and place. So how do you get away from the idea that you have to preserve everything everywhere?
Yeah, so that's where, you know, again, to use the analogy of the financial system, you know, you put it in a sort of a risk per reward basis. And that, you know, how much, you know, yeah, you and I can say they should conserve everything, but that's not logical, right? So instead, we should be putting out, you have a hierarchy. You roll out a menu to the policymakers and say, here's our best estimates of the risks and rewards of doing different levels of protection, for instance. They get to decide that. We don't get to decide that, right? And the truth is, the bigger the chunk of the landscape you protect, the more diversity and probably the more stability and reliability you'll have in it. But of course, you can't protect anything. So the question is, how much farther are you allowing it to erode? In the case of Pebble Mine, I think I was talking with Chuck about this, you know, in assessing the risks of Pebble Mine, what most people focused on was the pit and the storage facility for maintaining tailings. And that's what most of the risks were associated with. And what we pointed out was, well, hang on, can't forget about the rest of the watershed and the roads that go in and the pipelines and the power lines, because what that does is erode the habitat at a sort of more diffuse scale and changes the risk of that development project. So yeah, you're right, you can't protect everything, but you can also think about it the trade-off between risk and output.
I have a question about the relationship. What do you, for example, we think of a food web, low-trophic pipeline contribution to important to control the fish population. We think there is a link between the lower trophic level and high trophic level population.
Mhm.
During the fish.
So I think the question is, do the lower trophic levels cause some of those changes? Probably, based on first principles, based on what we know about how ecosystems work, those were probably the mechanisms that caused those regime shifts. The reality is this is a huge, huge ecosystem, and the best data we have are from what's been harvested out of it. And this is one of the reasons we're really limited in terms of understanding what caused those changes, is because we can't really sample even a simple river watershed. Is really hard to get really broad coverage on all the mechanisms that could cause change. You go to a coastal system like the Gulf of Alaska, and we should be pretty dubious that we can really understand how lower trophic level changes translate into upper trophic level changes. So, there's a bunch of stories that have been put forth to describe why this regime shift happened. But if we go back to that Ransom-Myers paper, that's a good indication or a wake-up call that we should be careful about putting too much confidence in an explanation that seems to fit the data. Ecologists are good at this. We see some pattern of change, we construct a story that describes that pattern. It's pretty rare that we go back and revisit it 10 years later and ask, did it hold up? Here, we don't know what the mechanisms are, but the data in terms of what was caught from the system are really good because they have to report what they catch. I don't know if that answers your question. Well, lots of people are writing proposals that are saying just that. We need more oceanographic surveys and tens of millions of dollars. And you can keep pouring money into this and keep doing lots of expensive research. The question is it really improving reliability, and is it improving policy and making those fishery resources more resilient and more dependable to the communities? I'm not sure it is. It's good for science, but I think it's there's a point of limit of diminishing returns.
So if you found that the work you've just done and the way you presented, is that influencing management of populations in Alaska or fisheries in Alaska?
It is in some ways. One of the interesting things about Alaska is with what's it called, Alaska Native Settlement Claims Act. The native corporations are sitting on tons of money. Some of those corporations are sitting on millions, if not hundreds of millions of dollars, okay? And one of the questions they are continuously making is, how do we invest those dollars in our community? And they'll, build a better firehouse and a better school and put blacktop on the road and these sort of things, which are little pieces here and there. But for the fishing communities, they're really concerned with how do we maintain fishing as our identity and as the foundation of our economy. And the typical thing is to continue to invest in boats that harvest the local fisheries. But part of the message we're giving them is, well, maybe you should think about how do you distribute your risk so that you can buy permits in, say, if you're in Bristol Bay catching salmon, maybe the thing to do is buy up some permits for halibut that fishes in Southeast Alaska. And some of your fishers can go down there and fish halibut in Southeast Alaska when the local salmon stocks, bust for a few years. So the message to them is think about ways, because they are diversifying to other sectors. They do use that money and they invest in mining of all things, and oil and gas and tech and who knows what else. But they're also really concerned about losing their identity as fishing communities. So part of the way to maintain that is to diversify what they fish for.
racially flexible, isn't taking as big a cost as it will ultimately. So their fishermen who aren't doing well because, the African mackerel go by, but they can't take African mackerel there. The African
Yeah.
mackerel aren't where they're supposed to be.
Yeah.
Because the waters are warm and cold in places they aren't supposed to be. So is it just the good luck of a relatively low human population density? And even though the fishing is pretty high, it's not as high as it must be.
Yeah, so I mean, for most of these fisheries, Fish and Game has done a really good job at fishing for maximum sustainable yield. And in many cases, they're exploited lower than is necessary to get to maximum sustainable yield. And the question about, it is a fluke here that there's probably more diversity here than there would be if it was totally developed. So if you take salmon alone, because that's where the good data are, a lot of the diversity in the lower 48 has been stripped out of it, whether it's genetic diversity or habitat diversity. Alaska still has all that, and they're not exploiting it explicitly, they're exploiting that diversity implicitly. It's been a fluke, but this is where some science is saying, well, hang on, guys, this is the reason why you've been sustainable, is because you've benefited from all this diversity, which means protect the habitat, and even though Pebble Mine is telling you we're going to hire 100 of your folks for the next 50 years, that may be seductive, but you got to trade that off against what's it worth in terms of maintaining the habitat and reliable fisheries. Or in places in Southeast, communities like Sitka, for instance, in Petersburg, where there's a lot of wealth in fishing communities. The reason there's wealth in those fishing communities is because they've diversified across a whole bunch of species. And they always have a good year. It just may, the year that's good for herring may not be the year that's good for halibut. So a lot of these things people know, and communities are exploiting implicitly, but it hasn't become an explicit part of their strategies for dealing with global change, and they're all worried about that.